Okay, so there was some problem with my computer. Okay, so I'll just start from where I. Okay, so okay, so as I said, vibration isolation basically means isolating the system from the surrounding so that no vibration can be transmitted. Okay, or we can also say that isolating the surrounding from the system. Like for example, if I have a system, okay, and within that system I have some component. Let us suppose A. Let us say, okay, I have this system. Let us say A. Okay, and I have this component B on it. And then I have a sensor placed like this on B, which is C. Okay, my C is a sensor. And this sensor is actually sensing the vibration which is happening in the system B. But now my this system A, due to some reason or due to some fault in its components, it starts vibrating. So what will happen? Now the sensor C is going to sense the total vibration, means it is going to sense the vibration of B as well as the vibration which is transmitted to B because of A. Correct. So in that case, I need to apply some isolation over here between A and B so that B is vibrating only because of its nature, not because of the transmission of some vibration which is produced in A. Because see, if I'm not going to isolate B, then I'm going to see that my B is actually vibrating at some other frequency, or maybe it is having two frequency components, which is not true for it. Right. So that is why some kind of isolation is required. Second comes vibration absorption. Now, vibration absorption means that I apply some absorption technique, like I apply some viscoelastic material or something of that kind, or rubber, for in order to mitigate the vibration. Okay. So what would I do? I would dissipate the energy into some other form, which is generally heat, isn't it? Which would generally be heat, right? So this is the case. Now further, your vibration isolation can be further divided into two categories. Okay, one is the force isolation and the other one is the base isolation. Okay, now if I talk about force isolation, what does it mean? It isolates the force. Simple. So it would isolate the force, which may be like for example A, if it is vibrating, it is going to produce some kind of a force, right? Because of the vibration. So that force is isolated. It is not being transferred to B. Okay. The force is isolated. Okay. And base isolation is essentially used in, as I said, about some kind of a machines which have rubbers on its base, which is used for isolation of the vibration that is being produced in the machine. Okay. So what do? We basically decouple the surrounding. Okay. We would decouple the surrounding from the system. Now, this was about vibration isolation. Next comes the vibration absorption. Now, vibration absorption basically means that we would dissipate whatever the vibration is produced. Like, for example, if I talk about again a car, it has damping system, okay, through which the vibration is dissipated, right? It has a damping system due to which if the car goes by some bump, the vibration that is produced by that is not transmitted to the chassis of the car, right? So that is done by absorbing. Okay, so what happens is that if you know there is a suspension system, there is this yeah, suspension system. It is basically a type of a viscous damper. So what happens is that the viscosity of the liquid actually dissipates the vibration energy through heat. Okay. So now vibration absorption is further divided into four categories. I'll take another slide to explain. Now your vibration absorption is divided into four categories. Okay. Your first one is the passive vibration absorber. Now, why do we call it a passive vibration absorber? The reason is very simple. What would I do? I would introduce a system. In vibration absorption, what is my basic objective? My objective is to dissipate whatever the vibration energy is present in the system. Okay, how would I do it? I would introduce a system, maybe a spring mass dashpot system or something of that kind, which would actually dissipate the vibration present in the primary system. Okay, so now if I introduce a, for example, if I introduce a spring mass damper system, okay, then if I add a mass, let us say M2, and I have a dissipation C2, and I have a stiffness of K2. Now, the passive vibration absorber, in case of passive vibration absorber, once I decide M2, K2, and C2, it is not going to change. Okay, it is going to perform the absorption of the vibration based on its own characteristics or own properties, like damping property, stiffness property, and its inertia properties. Okay, it is not going to change with time, these properties. It is going to show the absorption behavior because of its own properties, and those properties are going to be the same. Yes, because it's a material parameter, right? So, in a passive system, consists of a system which we usually call it as a secondary system. Our main system is known as the primary system. Okay, so it consists of a system to mitigate the vibration. Okay, because of its property. So it actually operates on the concept of resonance and dissipation. Concept of resonance and dissipation. For now, for this line, uh, just understand that if I consider spring March dashboard system, it is going to show resonance, it is going to show dissipation, right? So if I introduce a secondary system which has a spring mass and damper, it is going to either change the resonance condition, it is going to either change the dissipation effect of the system, okay? And this I'll also show in the further examples that I have considered. Now, if one is passive, the other is going to be the active. The active vibration absorber, see, if in passive my properties were not changing, then in active, what would happen? Definitely it is going to change. So in active vibration absorber, what do? I introduce some kind of active materials inside the system. Okay, I can use a sensor, I can use an actuator like that, so that I can control the vibration of the system. So what happens in an active vibration absorber is that it produces and apply counter load, or it should be force, not load. Counter force to eliminate vibration. Okay, through feedback. Now, feedback, what does it mean? For example, if my system is vibrating, right? If I apply a sensor on it, let us suppose, okay, if I apply an accelerometer on it, what is going to happen? I can take out that how the system is behaving with time. I know how the system is behaving. What if at the current state, whatever the state of the system is, I take it from the sensor and I send it to a feedback loop such that now whatever the input is being given to the system, it now changes depending upon the whatever the system is performing, whatever the signal we are getting from the this sensor. Okay, so active vibration absorber actually works on that. What I mean is that it would apply, first it will produce and then it will apply a counter force such that vibration is eliminated. For example, if my system is going up, what would it do? It would apply a force in the downward direction so that this force, the force with which it is going up and the counter force, it is going to balance itself and it would remain at the position I wanted to stay. Okay, in case of a passive vibration system absorber, I was not able to actually take a feedback of the system. Okay, I had only some properties of the system, and based on that property only, it was actually mitigating the vibration. But in active vibration absorber, I have the freedom. Okay, I have the freedom because I have a feedback loop. It can actually be helpful in more like I would say dynamic cases, and it would also be helpful for a variety of cases, right? Because it can handle any type of a vibration a system is actually going through. While in case of a passive vibration absorber, we have like tuned mass absorber. We tune the mass and the stiffness depending upon what my primary system is. Okay, and then I apply it. Okay, but in this case, I don't need the tuning. It is going to change its properties depending upon the feedback. Okay, next come the semi-active. Semi-active. Semi-active, it is not fully passive and it is not fully active. Okay, so it basically takes the property of both your passive and active and then act in that way. Okay. You also, for a semi-active case, what happens is that, yeah, for a semi-active case, what would happen is that, see, in case of this active vibration absorber, what I was doing, I was taking the value from a sensor and then I was applying, the system was producing a force to counterbalance the vibration. In case of a semi-active, what happens is that I use a feedback loop, but with that, I would change the property of the system. Like in passive vibration, I had a particular property of the system, right? In active vibration, I was actually getting the final force which I wanted. In case of a semi-active, I have a feedback loop, but in this case, depending upon the feedback, I would change the property of the passive system so that it would help in mitigation of the vibration. So it is a combination of active and passive. And there is one more, which is fourth, which is the hybrid one. So hybrid also essentially has the passive and active both with itself, but it has the property like in semi-active, we were actually taking the feedback loop and we were changing the properties of the passive system, passive secondary system. In hybrid, we are taking both. We are having active vibration also and we are having passive vibration also. We are not having some partial effect Like in case of semi-active, we are having partial effect of passive, partial effect of active. While in case of hybrid, I'm having full effect of passive and full effect of active. Okay, so as the question says that which of the following is used for vibration reduction? So passive vibration absorber, active vibration absorber, vibration isolator. All the three are the correct answers. Okay, coming on to question number 2. So for a 2 degree of freedom system, the response amplitude for any forcing with frequency, this will be any external forcing. So this was also discussed in, I guess, week 1 or week 2. This thing was discussed. However, I'll still explain you what the system is, how it is behaving and everything. So, for example, if I have a primary system, I have a spring and I have a mass M1 attached to it. Right. Now, if a forcing is applied on it, let us say some F, which is a function of T, what is going to happen? It is going to vibrate at its natural frequency. Correct? If I talk about its amplitude frequency response, how is it going to be? First of all, what is going to be its natural frequency? So if I write its equation, for example, this is my x1, and if I apply force balance on it, my F is acting like this, and I'm going to have an inertia force over here, m1 x1 double dot, and I'm going to have a spring force k1 x1. Right, so my equation of motion would be m1 x1 double dot plus k1 x1 is equals to f, let us say a function of t. Okay, now I can divide this whole by m1, which would give me x1 double dot plus k1 by m1 x f by m function of t. Now this is my omega n square. Let us say it omega n1 square. So, or let us just call it omega n only. So my omega n is under root k1 by m1. And so if I plot the amplitude frequency response, it would be something like this. Correct? This will be my, okay. So this is how it is going to behave. Now, if I introduce another mass below it, if I make it like m1 and I introduce another mass over here, m2, I'm going to have k1, k2. Now, what are the probable effects it can cause? Intuitively, what can I say? So the probable effect is going to be first, now under root k1 by m1 is not going to be a natural frequency. Right, now the system is going to have, if you remember, if the system has 2 degree of freedom, so it is going to have 2 natural frequency. Okay, so the number of natural frequency would depend on the number of degrees of freedom. And for a continuous body which has infinite degrees of freedom, it has infinite frequencies. Right. So it will have 2 omega n. Okay. So what would be that omega n? Can it be under root k1 by m1 and under root k2 by m2? Well, that is not the case. We say that if this is my primary system, this was my primary system, this becomes my secondary system. Okay, so what is going to happen? I'll write the equations as of now, and I'll just tell you that they are going to be 2 natural frequencies, and that will not be equal to this omega n. So they are going to be 2 natural frequencies, right? And that would depend upon the system behavior, which I will show you in the further questions, that how are we actually evaluating the two natural frequencies and how is it different from under root k1 by m1. Right. So let us suppose now it has two natural frequencies. Let us call it as omega 11 and omega 22. Okay. So in that case, after solving the equation, and if I want to find out that what is going to be the analytical solution, because it is a linear system and 2 degrees of freedom, I can find out its analytical solution. So I'll not get into all the mathematical calculation, and I'll just write this amplitude as a function of, I'll write amplitude. It will be something like, now this is for if I assume my f of t is actually equal to f naught, let us say sine omega t. Okay, so my this amplitude would come out to be 1 minus omega by omega 22 square divided by, for this you can refer to any basic book of mechanical vibrations. There you will get this. Okay, k2 by k1 minus omega by omega 11 square into 1 minus omega by omega 22 whole square minus k2 by k1. This is my relation. Now, if you see over here that the question says that the response amplitude for any forcing with frequency this will be. Now, if you see, if I put omega as omega 22, what is going to happen? My numerator is going to be 1 minus 1, which would be 0, which means that my response amplitude would become 0. So, if my excitation frequency is equal to, let us say, omega 22, which is actually the natural frequency of, if I consider only the K2 and M2, and if it is equal to that, then what would happen? Then my primary system is not going to experience any kind of a vibration. So what have I done? I've mitigated the vibration. Just by introducing another spring and another mass, I have mitigated the vibration in my primary system. Now only my secondary system is going to vibrate. My first system is not going to, primary system is not going to vibrate, and it will remain in equilibrium, right? So it will be 0, firstly. Secondly, if I try to plot the new amplitude versus frequency response, it will be something like this. This is omega 22, and my omega 22. Okay, this 2 omega n is not omega 11 and omega 22. This is actually omega 1 and omega 2. And yeah, omega 1 and omega 22 are essentially the respective natural frequencies of the primary system and the secondary system, provided we consider that it is not attached to each other. Okay. So if you see, my amplitude frequency response now changes to something like this. So what has happened? Now, by introducing a new spring and a new mass, I have shifted my resonance conditions. Now, instead of one peak, I'm having two peaks. However, I can see that at omega 22, my system is not having any kind of a vibration, primary system, right? So the answer would be 0. Okay. And for this equation, you can take any of the basic book of mechanical vibrations, and there you are going to get that from where are we getting this. Okay. It is essentially given as tuned vibration absorber in the textbooks. Okay. It is essentially known as a vibration absorber because you can see that it has made the amplitude of vibration 0 for omega is equals to omega 22. Okay, now it says for the given system, find the modal. Okay, I have to draw the system. Okay. So you have to consider a system Consider a system like this. There is a spring, there is a mass, there is another spring, there is another mass. Okay. Now, if I take it as 2m, m, let us say 2k and k. Okay. So this is my system. Now you can see that it is a 2 degree of freedom system. Okay. So it is going to have two movements, x1 and x2. Okay. Now, if I want to find firstly the modal frequencies. Now, modal frequencies, why is it required? It is required so that I know that what are the frequencies, individual frequencies. Okay. So now why is the modal analysis important? What is modal analysis actually? What do we do is that when we see here that my equations are actually coupled. Right. My equations are coupled, which means they are dependent on each other. Through modal analysis, we try to decouple our equations and then try to find out that how the system is going to be. We know that there are 2 degrees of freedom, so it will have two natural frequencies. But how do I know that what are those natural frequencies? So that is why we do the modal analysis, and that is why we try to find out the modal frequencies. So firstly, if, if the system has 2 degrees of freedom, then it will have two natural frequencies. Okay, now if I try to apply the force balance, you can also take out the equation of motion by Lagrange equation or by Hamilton's principle. That is up to you. For now, I am taking the force balance technique. Okay. And once I solve the equation, what you can do is, as a homework, you can try to find out the equation of motion by Lagrange or Hamilton's equation, which I have discussed very thoroughly in previous live sessions. So it would also help you to have a practice of those two techniques. Okay. Essentially, the equation of motion which I get from force balance or Hamilton's principle or the Lagrange equation should be the same. Okay, there should be no variation in the equation of motion. So, coming on to force balance technique. Yes. So, firstly, I have a mass 2m. It is going down with x1. Okay. So, what is going to happen? This spring is going to apply some force on it, which would be 2k x1 minus x. No, it will be just 2k x1. And there's also going to be an inertia force, which would be m1 x1 double dot. Apart from this spring is also going to cause a force which would be k into x1 minus x2. I hope that this is clear. So in that case, first I'll draw the free body diagram of the second mass as well. Having x2. Okay, so what? If it is going downwards, it is going to encounter inertia force in the opposite direction, but will be m x2 double dot, and then there will be a spring force which will be k into x2 minus x1. Correct? From this I can get the respective equation of motion. I'll have m1 x1 double dot plus 2k x1 plus k x1 minus x2 is equals to 0. And the second equation would be m2. No, there is no point of m1, m2. This is actually 2m, right? And this is m x2 double dot plus k x2 minus x1. is equals to 0. This can be further written as 3kx1 minus kx2 and mx2 double dot minus kx1 plus kx2 equals to 0 is equals to 0. Now, if I have some equation in this form, what I can do is I can write it in matrix form, correct? How can I write it? I can write it something like m x double dot plus k x is equals to 0, where my capital M and capital K are mass and stiffness matrix. Okay, so what would my matrix be? Firstly, my X matrix is going to be x1, x2. My mass matrix is going to be 2m, 0, 0, m, and my stiffness matrix K is going to be what? 3k minus k minus k and plus k. Correct? So now I can write my equation as 2m 0 0 m x1 double dot x2 double dot 3k minus k minus k k x1 x2 is equals to 0 0 because it is in a matrix form, right? So this is my equation which I can write in the matrix form. Now if I'll just assume that my solution is in the form of sinusoidal form, let us suppose. Okay, so let us assume that x is equal to a cos omega t. This is going to be your capital X and not small x. Okay, and here your a is going to be a array, something like this, A1 and A2. Okay, so your mass M1 is actually showing a vibration of with amplitude A1, and this mass M2 is going to show the vibration with amplitude A2. Okay, now if I have capital X, I can find out its second differentiation with respect to time, right? So X double dot would be equal to minus A omega square cos omega t. Okay, if my x is a cos omega t, my x dot is going to be what? A. Differentiation of cos would be minus of sine omega t into omega. And again, if I do x double dot, it will be minus of a omega. Differentiation of sine would be cos omega t into another omega. Okay. So from this, we get this. Okay. Now, if I put these two equations in the main equation here, what am I going to get? So let us just see. I'll have 2m 0 0 m. I'll have a1 a2. Why a1 a2? Because this a is a1 and a2, this capital A, and my a1 and a2 are not dependent on time. Okay, so I'll get something like this, and then I'm going to have into minus omega square cos of omega t plus 3k minus k minus k into, again I'll have a1 a2 cos omega t, and this will be equal to 0 0. Now I can take common, right? I can take this as common,